Good afternoon, good evening. Another warm day in Colorado Springs, but the weather maybe is going to change. I don't know. I turned my sprinkler systems on yesterday because I'll just repump them up and then drain them again if it gets warm out. So we're here on the home page. The biggest news here is I did post set number 6. That covers all of chapter 5. That is what will also be on this second exam, and we're going to be done with it next Tuesday, the covering of the material, and you'll be able to turn it in on Friday. I didn't specifically say when it's due on Friday, but the sooner the better, because then I can post the solutions. You'll already have in your hands before Friday, is my anticipation, the take-home exam. So things will just move forward. I'm nearly done grading set number 4. I'm just got busy with other stuff. And set number 5, which all of you turned in since yesterday, that I'll post that up, but that's a pretty easy one to grade because there's not a whole lot there to go through. I've also posted a new notebook and PDF rendering for the chapter 5 Python stuff. So, and I'll be using that tonight, or start using that tonight, and you can download that newest version if you want to have it as a model. It has some examples of things for the homework, actually, some ideas for problem number 21, which is a really cool problem in chapter 5. Before I start going off on something, does anybody have any questions about our game plan? 1 week out, what is our game plan? You'll get a take-home exam next week, maybe Thursday. I've got to study my problems. You won't have an old exam for exam 2, but there is something on the website already that's going to help you prepare for that's up there in the materials. And I'll just say that typically exam 2 not only is the problems, it's got a backside of it that has lots of hints on it for the harder problems, the problems that are more experimental, the ones you'll do in Python. So the tradition for me has been that there's lots of material there because I know you're on your own, and I'm trying to just head you off at the pass, so to speak. You know, rather than you having to call me, hopefully you'll be able to find answers to what you're looking for. But that doesn't mean I won't be available. I'm not going to be going anywhere. So, as a matter of fact, I'm pretty sure I've been talked into teaching Com 1 next semester, or at least until I go on my first cruise very late in the semester. And from what I heard today, and none of you it probably applies to, it's going to be on Tuesdays from 8 to 10:40, and then the Com Lab will be right after that. I saw that negotiation with Chirant Sidiapa, who's teaching the lab, and that lab is going to get moved into this building upstairs here. So the lab you've been in, John, is going to be vacated ASAP. So I've got a number of demos. I've got four different software tools that I'll be using in the demos today, and we'll be wrapping up the material in chapter 4, and then we'll be starting in earnest in chapter 5. And what's left in chapter 4 is really just some details to talk to you about sigma delta converters, and also draw a connection between that and the homework problem that you worked a while ago that had, remember the homework problem with the block diagram in it? That was a model for the sigma delta converter, and we're going to see how that comes into application in this area. So the first thing I'm going to look at, and I guess I didn't get my stylus out. Hard to believe, riding my bike over here, it was more pleasant riding today than it was a week ago, and we're another week further into the winter, start of the colder season. At any rate, the first thing we're going to do is just motivate the idea of oversampling and trying to reduce the number of bits in the quantizer. So this model just says we have B plus 1 bits, we're heading towards having just one bit in the quantizer, if you can believe it, and we'll be able to get away with that because of oversampling. So here we're just saying we have a B plus 1 bit quantizer. We're assuming that we're going to have a downsample by m, so that we've oversampled by a factor of m. And there's a bunch of random process modeling in here. I put an appendix in years ago for this chapter that goes through continuous time random processes. I don't want to burden you with learning the details because there's no homework on it. I mean, if you were to take some other class somewhere, and I say somewhere because the classes I used to teach, but classes that haven't been offered definitely for quite some time, you'd get introduced to it. And if you wanted to see a more rigorous introduction to it, you could always go look at 5630. So you could go over to here, 5630, Com Systems 2, and it starts with probability random variables, and then random processes. So there's a whole chapter on random processes in here, and this is primarily from the continuous time point of view. So that is right there. So make sure I'm back where I need to be. So the model that's put together here is to say, okay, we come in with the continuous to discrete converter. We're assuming that our sampling rate is m, an oversample factor of m, and we have this error sequence down in here, which is representing the quantization error that happens with the A to D converter. So we have the additive noise model for the quantization noise. Then we're going to low-pass filter as a pre-filter to the downsampling by m. And of course, in reality, these two blocks would be done as a polyphase, like we've already talked about, to make it more efficient. And the figure of merit is the signal power at the output over the equivalent quantization noise power. So that's a measure of the quality of the conversion process. And you did in homework problem 3, you experimented with doing those calculations. Remember, signal power, quantization noise power, and then the ratio. So the analysis here is kind of similar. We're going to assume a triangle shape for the spectrum coming in the analog domain. As it comes out to the discrete time domain, it'll have the oversampling by m, so it's effectively shrunk down to a bandwidth that's pi over m as a result of the downsampling. And we can calculate the power in the signal, and then we go after calculating the power in the noise, and I'm just sort of highlighting it here. And that's these two calculations. So mean squared value is the power in the signal, and for the power in the noise, it's based on delta squared over 12, assuming a white sequence for the quantization noise, and then that becomes a spectrum that has a spectral height of sigma e squared, the noise power variance of the noise. So when we're looking at what it looks like at the front end to the system, we see, or at the front end of the system, when we have the quantization noise as a flat spectrum, the shaded one, and then we have the power contained in the signal, which is that triangle shape. And then after we downsample, what happens is, and this is the important thing right here, we've got sigma e squared noise power, but when we downsample, we're only going to pull out of that and this is just from the downsample attenuation effect. We're going to see the spectral density lowers by a factor of 1 over m. So just oversampling reduces the noise power when we go into the downsampler, and the observation here every doubling of m increases the effective number of bits by 1/2, just because you have that factor of m in the variance of the noise. The problem is it's not very big. Suppose you wanted to go from, say, 10 bits to 16 bits effective due to oversampling. My watch was binging Sports Star Dead at 70. I always get alerts like that. I'm not really worried about it, but some of you have alerts turned on too, right? These were turned on by default, but I sometimes look at them. At any rate, if you wanted to get a significant, like 6 bits, you would have to have 2 to the 12 as the oversampling factor, and that's monstrous value of oversampling. So what somebody who was very smart figured out probably in the 80s sometime, 80s or 90s, that they can do what's called noise shaping with the oversampling. So they can combine noise shaping with oversampling, and this became the generic delta sigma or sigma delta. The two letters there can be turned around, A to D shown here. So you come in with a switch capacitor integrator, and we'll have a model for that in a second. You go through an A to D converter, and then you feed back through a D to A converter an error signal that gets subtracted from the input, and that action is the action of the delta and the sigma together. You're summing in the switch capacitor integrator, so that's where the sigma part, or the sigma corresponds to the integrator. Sigma would be like the capital sigma for a summation. Think back to our notation, and that would be like in continuous time domain and integration. And the delta would be having a difference between the input and a processed fed back output. So that's, in my recollection, that's where the delta sigma idea comes from. It's composed of a delta block and then a sigma block. Because what is a delta? It's like a difference, and that's kind of like a derivative. What is a sigma? It's a sum or an integral. So we differentiate, then we integrate, and we're kind of haven't done anything with the signal, but we're going to see that this does do something to the noise. So here's a behavior level model in the discrete time domain. It says we're going to have this for h of z for our sigma portion, the integrator, and what, after all, what is this from way back when? This is the accumulator, right? 1 over 1 minus e to the minus 1 is our accumulator, so it's definitely a sigma type operation, a summation operation. We have the difference, then we have a quantizer of so many bits, and then we feed back, and in order to be causal, we have to feed back with at least a 1 sample delay. So we have a 1 sample delay in the feedback path to form this delta. So in the real hardware, the switch capacitor integrator is an analog function block in analog IC design. Here it's just replaced with a simplification for the discrete time domain for modeling it. So what we can do with this is if we use our simplified noise model to represent, the quantization noise is additive, we can go here to this quantizer and say that quantizer is really just the signal alone coming in, and then we're going to model the quantization noise as we have since last week, where we just have a uniformly distributed noise coming in there. Is that acceptable? To say we're going to replace a quantizer with the ideal signal plus an error signal that represents quantization. Simple idea, and this is, I don't have the knowledge to go deeper than this, because this is all I've ever studied since I first was teaching it. I did have somebody a long time ago in this class who was a mixed signal IC designer and he was very knowledgeable of these types of converters and made the class interesting for me because he knew more about this than I did for sure. At any rate, now we're in a position that this looks like the homework problem just a little bit. The homework problem was really just this part in here. It had an input, it had an error signal, and it had, I think this was H1 and this was H2. Is that right? So this is, the authors of the textbook threw that in early to get excited about this. And then here, this is just the anti-aliasing low-pass filter and the downsampler. So this was what we had in the homework problem, exactly. Then make the substitutions in there, and we see that the net transfer function for the signal component, you know, the one that comes in across the top and gets this feedback, it's flat. So there's no frequency response shaping in that. And then the error signal has got effective transfer function, and this was also in the homework, if I remember right. This was exactly what you played around with. Is this stable or not? This is an FIR filter. It's a backwards difference operation, present minus one sample in the past. So if we redraw the block diagram one more time, we've got quantization noise comes in and goes through this backwards difference. The signal comes straight on through, no alterations. So now what we do is we model the input signal and the power coming out again just like before, the mean squared value. And then we're going to have white noise going into here. This is our white quantization noise, uncorrelated from sample to sample. And then it gets shaped by the frequency response magnitude squared. Remember this power spectral density theorem. It's also something you worked with in problem set number 5, right? Second problem. This was part of your calculations, remember? It's actually very similar to this, I think, because that's another problem that's a little bit related to this theory here. At any rate, that's the frequency response, sine squared. It goes into the integral to calculate the mean at the output, or the power in the error signal. Let's see. Yeah, it's the integral. So we're integrating the power spectral density of that white noise driving that 2 sine omega over 2 quantity squared filter. So this is the value of the spectral density, and let's see. Yeah, it's noise spectral density contained in E hat of n. Getting myself a little bit confused. It's at the output here of that filter. But now we're going to go for the total noise power, which is the integration part of it. So this picture really tells the story, and I'm not trying to get super detailed on this, but this is the noise power from the quantization noise. It's flat. This is our signal that gets processed out through the narrower band because of the oversampling by M. But the way I like to think of it, as the signal comes in, the noise, quantization noise comes in, it's flat. And what the shaping filter action does is it pushes the noise down around DC in this neighborhood, and it pushes it up higher outside of that. So it's like the noise comes in flat, it gets squashed down, and it's like, I don't know, a rubbery surface or something. You're squeezing it down, and the volume has to stay the same, or area has to stay the same in this case, but it pushes it out to the edges. And then the filtering action of the downsampler of course, throws all this away, and we're left with a smaller amount than what we started with because of this noise shaping idea. And if you kind of zoom in on it more, I drew it a second time. This is what the spectrum of the signal and then the spectrum of the noise looks like. And if you integrate now, finally, this is an approximation to that integral, where you assume that M is large, so you're working with a sine of a small value, or which is that, right? Standard thing from physics or anywhere else in fields or anything like that. You might use that approximation. So now we put that together with the signal power and want to compare, and the way I did it and the way the book does it. This says that every doubling of M is equivalent to a gain of 1.5 bits. Much better than what we were doing before. And so this is a table that I think appears in the book. It's at least what I put in my notes. As M rises up, the effective, this is direct quantization just with oversampling. This is with noise shaping. It increases it by this additional amount. So this is kind of what we're after. What is the amount we're going to get? And what people were driving for was M is equal to 64, 64 times oversampling. So with a single integrator, you can't get there. So what you have to do is go with higher order noise shaping, and this is a cascade of two of the integrators, and this gives you, that noise spectrum is shaped to the fourth then. And if you in general go with P stages in the noise shaping filter, you get that raised to the 2P. And when you finally put all of this together, this table is like, what is the order of the filter, and what's the oversampling factor? This is what people were looking for when they came up with this. This is 64 times oversampling with a third order noise shaping filter, and that's the number of bits equivalent that you're at when you start off with a 1-bit converter. So that is achieving the 16-bit equivalent accuracy is where I looked at it when I first read about this. It says it's equivalent to 18.45 equivalent bits. The analog IC designers had to figure out how to make this thing stable. That I know is one of the factors. All I'm doing is relaying to you that this is kind of like a significant thing that came into being, especially for audio converters, things that we use all the time. Anything you listen to like through a headset like this or earbuds, anything streamed off your phone, it's all going to be using a converter that can take advantage of this capability. And you can turn this around and make it a D to A converter. So this is the input side. You can do the output side with the exact same kind of approach. So this is just looking at it briefly going backwards, but I'm not going to spend really any time on it. We've got a lot of other things to talk about. I'm not an analog IC designer. I did have one class in it as an undergraduate, and we had a lab that went with it, and I had fun. I'm an electronic circuit designer from the very beginning. That was what my job was. That's what I wanted to do, because remember I told you last time I didn't take any DSP as an undergraduate or in my master's. I just wanted to do electronics, plain and simple. If my parents were alive, they would say, I come from a family of 4. What was I crazy about as the mad scientist in the basement playing with stuff? It was electronics. I was kind of infatuated with it. And Radio Shack was my favorite place to go spend money at. But not for, like the CD player I mentioned, I did buy there, but usually it was buying components, breadboards, all the stuff that is the norm in electrical engineering degree program. So I don't know if any of you think that way, but I got into DSP slowly but surely. My first job was a board level designer, so I was doing electronics, plain and simple. It was digital, microwave, and linear analog electronics, all kind of rolled up into one thing. It was fun being a board designer, but not very many people get to do that anymore. It's like people have to come up, I don't know if you've thought about this, and in capstone design, I think you do get trained on this. What is the thing you have to do if you're doing a design and you're implementing something on the board? You have to have a schematic, right? So how do schematics come together? Everybody that's on the team has a portion of the schematic, and then the schematics go together. Or when I worked at Motorola Government Electronics, my schematics were a whole module. So they were a PCB that maybe was that many inches square, and another guy. And then it was put into aluminum machined modules, and then those were stacked up into the chassis, and there were SMA connectors going around and semi-rigid coax connecting everything together. That was in that generation of electronics. Pretty old, but to me it was impressive. It was lap soldering or surface mount parts everywhere. That idea of lap soldering probably doesn't even get mentioned anymore, but that's what they called it where I worked. It became what is called surface mount. So without going any further, I'm just going to exit out of here. I will go back, since you weren't here last week, John, and look at the fact that in the board that you've been using, this is the type of thing that's inside of it. And if you look at the specs for it, it is doing, it doesn't say so right here, I thought it did. It's doing 64x oversampling. I was thinking it was in there, but it's not. So, and that's the converter that is on there. That's this part right here. So it changed everything, and I'm happy with it. Now when you get involved with digital radios, the space radio project I worked on, the A-to-Ds aren't sigma delta converters necessarily. There's something that can clock at over 100 megahertz, so they probably don't, we've approached that certainly in specific applications, but it just depends on the application area, what it's going to be. But there's bandpass sigma deltas, for example, that are out there, and I know Analog Devices pursued that, and they have that in their portfolio, since I worked for another company here in town that was working on bandpass sigma deltas, and they could be used in software-defined radio. We'll get into that a little bit for the final project. I've been playing with a new SDR that I bought about a month ago, and I'm going to try to capture some better data, better waveforms for that experiment. So any questions on this? Just as a point of interest, if somebody says, have you ever heard, do you know what sigma deltas are? I want you to be able to at least say they're a major impact on our audio electronics, and even higher than that. So before we jump into this, I decided I would try to get something in Julia working, because I realized I had a pretty neat demo that I haven't been able to show off yet, and I never was able to show off Julia. So this is what a Pluto notebook looks like. Remember, I mentioned this in the very beginning, and we decided we're just going to focus on Python, so I haven't pushed any Julia onto you. But Pluto notebook has some nice features, but the important point to notice at the very top is you import things into a Julia notebook. You can do Julia notebooks right in the Jupyter environment itself, or you can use this Pluto notebook, and there's a couple others that have since come on the scene. So this is just the way this notebook goes together. Now, what makes this notebook special is it's what's called a reactive notebook. So you put any cell down, and it very carefully looks at what you're typing into a cell, and if you reuse any code variable name anywhere, it will get very angry with you and say, you can't do that. You have to make every variable unique, because what the Pluto notebook wants to do is react to anything you do in a cell. If you're using a variable elsewhere, it will use that value, and if you go up anywhere else in the notebook and change that value, it will go into the cell you just created. And I don't know, how does that grab you? Because depending upon how you write notebooks, my guess is in Python, you reuse variables and you don't really worry about stomping on them, changing their value, pretty much. I mean, you can do that in C, too. C doesn't really. If you change the type of a variable in C, then it's kind of a nasty thing to do, right? Change it from a float to a character or something like that. But so what Pluto notebooks allow you to do, though, is you can create interactions where it takes advantage of this. So in this case, I have this GUI up here, and this is going back to the anti-aliasing filter that we talked about, I guess it was last week. And the way I can see what my code is, I can expose it. I have it hidden away right now. This is just Markdown. Pluto does Markdown differently. You start with MD and then put things in quotes. But here I'm accessing certain elements in this notebook, and you can see I've imported the Pluto UI package. And if you do using rather than import, that just means that all of the variables associated with Pluto UI are now available in the code base. I don't have to prefix them with Pluto UI. You know what I'm talking about? You do that in Python all the time now. You import SIGSYS as SS, and then you have to prefix the use of functions inside SIGSYS with SS dot something. Julia works the same way. But Julia allows you to import everything just like we're doing with the asterisk for all of NumPy and things like that, by just saying using, I'm using it. Here I've imported the plots package. I'm not going to use pycall. This is a way of calling things into Python. A DSP package, a polynomials package, and a FFTW for the FFT. Packages are organized differently in Julia. Julia has this standard, though, that package names have to start with a capital letter, so you can discern a package name. It doesn't say you can't have more caps in it, but it has to start with a capital. So at any rate, in this case, I've taken advantage of some of the functions that are in the GUI package for Pluto, like sliders, and that's what I'm doing here. And then I'm binding. This is all learnable by reading about Julia. I'm binding variables that are going to be inside my Julia code to the outputs of this slider. So this slider runs from 1 to 8 in steps of 1. Now, if you're looking at this and you're remembering how MATLAB worked, this looks very much like MATLAB's syntax, where you want to create a range of values, and you start at a value, you put a colon, and then put the step size, and then put the end value. That's the way Julia works. As a matter of fact, Julia works with a 1-based index for all the arrays, just like MATLAB. Kind of drives you crazy, because if you go to the two environments, C and Python, 0-based, Julia uses 1, Maxima or WX Maxima uses 1. It's an old language. I don't know why the inventors. This was invented at MIT, though. So at any rate, this is how I'm getting some sliders in, default values, display values. So those are all things I wanted up here. So this is just modeling the anti-aliasing filter as a variable order filter, like a Butterworth filter is what I chose here, changing the oversampling factor, changing the cutoff frequency of my anti-aliasing filter, and then this slider here just simply allows me to control a threshold. And it's kind of jerky here because good old video capture is running on my lowly PC, so it's not doing all that well. But so what is the code inside of here? The code inside of here is just simply something that's going to sweep over a range of frequencies and do some plotting. So I'm creating, I'm actually, yeah, I forgot I did cheat in this. I'm going inside of Python and getting access to its Butterworth filter because I knew about it. I'm going inside Python's signal package to get access to freq s because Julia can talk to Python. And what do you suppose? Python can talk to Julia too if you wanted to. But because I've been using Python for a very long time. When I first started playing with this over 2 years ago, I had to get access to a few things that I knew, and I leveraged myself up more rapidly this way. At any rate, those are all the calculations. So, but I just want to concentrate on what I can show you here. So, if we don't use any oversampling, and we want to get good rejection, you can see we don't get very good rejection, say with just a fifth order filter. We have to put a much higher anti-aliasing filter on, and that's what this is showing you, how I can get it down to that 70 dB rejection level for where they cross over here. Remember this picture? Is this foreign to you? This is our band of interest, and if we're sampling at a 1x rate, in this case, that's n over equals 1. Our spectral images are at plus and minus 1 and so on, and the alias components are going to sweep down and cross into our band of interest and cause aliasing. So I can resolve that if I make my filter have a narrower cutoff, a very narrow cutoff. If I try to reuse all of my band up to, say, 50%, or the folding frequency, I'm not doing so good anymore, and I'd have to, make a higher order filter. But now we want to see, just explore, if I make the oversampling factor go up to 4, which is what we played around with in that one example, now I can take this way down. Maybe not as low as you would hope for, but you can take it down, and it'll roll off naturally with much less effort on this filter. I don't take this down to first order in here. I guess I just didn't put that variable in there, but just a way of exploring. And when my dream when I first learned about this was I'd make everybody learn how to use Julia, and then they could make things interactive, and they could really dream a lot. I know, Miles, I've had discussions about how you like tinkering, so this is definitely a higher level. You can dream a lot, but it has its downsides. This language is a lot more rigid. It's not nearly as, Python is pretty permissive. It lets you get away with a lot of stuff without complaining a whole lot. Julia is a lot pickier because it's a faster language, and it tries to make sure you use types as much as possible. So this one is the reason why I put this up here. This is the quantizer equation that you did in homework set number 5, but this has got a simulation model under the hood. So under the hood here, what I'm doing is I'm generating 100,000 samples, and I'm running a cosine wave through a quantizer, and it just so happens I'm going into Python here also, Simple Quant, the one that you'll have available, and there'll probably be at least one problem on the exam too that will involve something kind of similar to this. So that's why I'm showing you this. So I'm doing that to get a spectral estimate, and then I'm also using the simplified model for the quantizer is just pure additive noise, and then no noise whatsoever. So right now I don't have the quantizer or the noise model turned on, but I can change the frequency around, and it's just moving around in frequency slowly and jerkily because of my computer here, and maybe I'm going to make it crash here. I hope not. So I'll turn on the noise model, And this is just the additive noise in place of the actual quantization. So turn on the quantizer, and I'm getting kind of a messed up looking result. So I'm going to pick a different frequency if I can. There. So now you can see this is from the true quantization model with a sinusoid, and this is the predicted from that additive noise model. Kind of similar, but what I'm wanting to show you is that when you're using a single sinusoid in a quantizer, you can very easily generate spurious responses. So by just changing the frequency, I'm just moving it here a little bit, it has kind of an erratic behavior. And a lot of times in systems they will use a dithering operation to just put a little bit of time dither into the waveform so that it's not so sensitive to the spurious responses. And this is the spurious thing we're seeing right here. I would not trust measurements I'm taking on my system with that type of response. So if I give you a problem that involves this sort of calculation, I'm probably going to say, I want you to move the frequency around just a little bit from what I tell you to use, and so you can get the spurious stuff to go away. And that would just be something like that. This would be more acceptable. And it's also sensitive to phase, too. If I change the phase of the sinusoid, it's going to change a little bit. But the encouraging thing is it works quite well. I didn't put in the noise power to raise and lower that, but that could have been another slider in here. Is this making sense to you? You know, we know noise exists in our lives, in our world. So this is the floor. Is this audible? Maybe not. If we go down into here, 90 dB down, that's what our music is generally trying to achieve, somewhere down in here. But this is just showing you the difference between the model, simplified additive noise model, and the actual quantizer. So I'm very likely going to have some problem involving something like this. And it'll be in Python, though, where you'll get to explore something. Other than that, that's really all I wanted to show you. There's the histogram that's being calculated. I think it's on the fly also. Takes the error that comes out and generates the histogram on the fly. And it also, let's see, it's very similar to the model that's available in Python. It lets you put in this normalized true. That's giving you a probability density function scale value. Safe to say it's got features MATLAB, Python, Julia. All these modeling languages have similar libraries and things available. Python is extremely rich with developers. Julia not as much, but it's growing. You'll have to decide. They won't let me use it where I'm working right now. I like it because it's faster and it's maybe cleaner in some senses, but it is more frustrating to program in it. It's very easy to make a syntax error, and it's very easy to read, you know, how you read in Python. What did I do wrong? Python puts up a pretty verbose display, right? And when you first saw that, you probably were like, what did I do? How do I fix this? And you've learned to look to the bottom and try to work your way from the bottom up. Julia's is just harder to really understand. It's got language features that require you to be more sophisticated, is what I'll say. Okay, so ready to get going on the next chapter. So this chapter is probably my favorite chapter because it's now bringing everything together that you've learned, and it's now introducing some new concepts and properties of LTI systems that you've never seen anywhere in the past. You haven't really dealt with them, so it's expanding your understanding. So we'll go through things related to frequency response, then drilling into system functions in more detail, geometric evaluation, what it means to have an all-pass system, and that's motivated by this topic 5.4, which is also special, the relationship between magnitude and phase. You've thought magnitude and phase are just what you get when you build a linear constant coefficient difference equation or ratio polynomials, but what is the relationship between them? So we'll explore that. All-pass systems come into play there, and then that also leads to understanding what it means to be minimum phase. And frequency response compensation. There's a topic in here that gets that going, the inverse system idea, and we'll see that, and then it gets explored further down, and I have that in the Jupyter notebook already. But what is an inverse system? It's if a system distorts something by filtering high or low frequencies away or putting a dip in it, can you build a filter that will flatten it back out again, equalize it, right? So that's what the inverse system idea is. And cellular telephony tries to do that. If we're in a bad multipath environment, it will measure your channel, and it will figure out what do we need to do to unravel that a bit so that we can get better performance in terms of lower error probabilities, higher quality of the voice call. I would say when you do a voice call, you don't really care about how many bit errors are involved coming out inside of your receiver. You just care about how can it be decoded through the synthetic speech vocoder to sound decent, right? If the call is getting flaky sounding, you're breaking up, it's sounding really awful. So it's trying to do something to measure the channel. But when you're traveling down the freeway at a high speed, it's more challenging to understand your channel. And then we'll get into a really big topic at the very end, but that's not going to be tonight. That's going to be linear systems with generalized linear phase, and that will lead to a class of filters, the linear phase FIR. Okay, the first little bit of this is just all review, and this is simple concepts. We started off with having a purely time domain characterization of an LTI system. We put an input in, we know it's impulse response, we get the output, and we have the convolution sum as our means of doing that calculation. So that was like the very first thing we were doing. The next thing we did is we went to the frequency domain, and we said, well, we could Fourier transform the impulse response, and then we can work with the input spectrum and the output get the output spectrum, and then inverse transform that to get back to the time domain if appropriate. Then the third thing was working in the Z domain, taking the transform of all quantities and working with X of Z, H of Z, and Y of Z. So these are the bread and butter properties that we have. If I was to vote, ask you to vote, I would guess you'd probably say you like this one the best. Okay, working in the frequency domain though, because that's where we understand at least signals and systems, and communication signals and systems is my primary interest, so I need to be in the frequency domain. But you're probably also comfortable with the idea that if I have H of Z, I can just replace Z by e to the j omega, right? I can use the freq Z function and sweep it and get its magnitude and phase. So now we're going to switch to distortion types. If we have a frequency response, magnitude and phase, what constitutes distortion? So the distortion we're talking about is magnitude or amplitude distortion, and secondly, phase distortion. So the amplitude is a function of frequency and phase is a function of frequency is not inherently bad. It's just if you wanted to pass a signal in this band of frequencies and the amplitude was fluctuating all over the place, you would probably say this is not good. Or if the phase is shifting a lot over that band, that's also not good. Now, since I play, like in the orchestra I practice with on Sundays regularly in the afternoon for this Christmas cantata, if amplitude distortion seems really obvious, but is phase distortion necessarily something you've ever thought about in a practical setting? I mean, I have to think about, well, where does phase matter? And a long time ago when I was really stereo, speakers and amplifiers and records and music, whatever, they always included a phasing switch on one of the audio amplifiers I had. So you would drive your right speaker with the wires connected like this, and then you would drive your left speaker with the wires connected in the same way, but then the phasing switch would take and flip one of the two speakers' wires around. Has anybody ever tried that before? If you were hooking up a stereo with speakers and wires? Well, when you have that phasing switch available, you can be listening to the music, you could be standing right in front of it, kind of equidistant from the two speakers, listening to a piece of music. You could flip that phasing switch, and basically what you're doing is you're putting 180 degrees of phase shift on that one channel, and the other one's not going to phase shift. So when you do that, flip that switch, it definitely sounds different. The question in your mind is, what is it supposed to sound like? And I'm not no expert on it. I probably, when I had the opportunity to do that, growing up playing with stereos all the time when I was in high school and college, I just decided which one do I like better, and that was probably how I left it. If you were ever wired up a stereo system with speakers these days with wires, you would probably just put red to a red connector and black to a black or something like that have plus and minus or something coming out of the power amplifier. So you wouldn't have that question in your mind. But I'm saying that because phase distortion might mean that there's an unwanted phase shift, and as it goes up in frequency, it might mean phase gets shifted in the way one particular part of the orchestra's instrument is sounding, and there's a lower pitch that's coming out that's supposed to be forming an overtone or a harmonic to blend and make a chord sound or a pleasant sound. If the phase shift in the amplifier is rotating it, it's not going to combine and sound as nice or as natural as what the intent was when it was recorded. So that's one example of phase distortion. A more extreme example in digital communications is phase distortion is making bits in error because you're now introducing some form of distortion in the amplitude as a result of the phase, and you end up making more bit errors. So there's actually a characteristic in high power amplifiers that are used in satellites and in your cell phone. It's called the HPA. The HPA was originally in satellites the TWT, traveling wave tube amplifier, TWTA, and it had characterizations as in how does it convert an amplitude into a phase shift, and how does it convert an amplitude into an amplitude variation. So you have this characterization called AM to AM conversion and AM to PM conversion, and that's a measure of the distortion that the amplifier puts in, both in amplitude and in phase. So here's 4 basic types of filters: low-pass filter, This is just the idealization of filters: low pass, band stop filter, high pass, band pass. I would say most of the time, these are the two that I think about dealing with the most, is the low pass and the band pass. But they all have their purposes and needs depending upon the application. So we'll be referring to ideal filters just as a reference. We know that we can't build any of these filters that are causal. They're computationally unrealizable. But still, the concept exists that if we could, we would choose to only pass certain frequencies and block the unwanted frequencies. So how close to this ideal is kind of what we get into. And there's this theorem, Paley-Wiener theorem, which I think is kind of an abstract thing to talk about, but the end result is going to be really meaningful to you. If we assume that an impulse response has finite energy, which is any passive filter, that's not got a electronic amplification side of it, and it's causal, so its impulse response is 0 for n less than 0, then it says that the integral of the absolute value of the natural log of the magnitude of the frequency response must be bounded by infinity. They're saying, I can run that equation out. Does that really have meaning to me? Well, the important thing that I get out of it is in this bullet right here. It says, if there's a response of the system that is 0, the response of a system can be 0 at a finite number of frequencies, so that the natural log of 0, which is minus infinity, right? And if the magnitude of that is, so it's plus infinity, then that's okay, but we can't have 0 over a band of frequencies. That did a very good job of underlining that. But that says, definitely it says we can't build a filter like this that passes and then perfectly blocks. So that sort of sets limits on what we can do, but it's possible to design realizable filters that approximate ideal filters just the same, and this is one of the concepts for digital filter design and analog filter design too.
I'm just wondering how that follows. Like, why can you have 1, 0? Wouldn't that go up to infinity then?
Well, the Riemann integral is what I'm thinking of from calculus. If you have just isolated points, you can say if you integrate that, you could ignore that point, because you can say how can one point, if you're integrating, right, it might go to 0 at a point, but if you're thinking of integrating at that point where it nulls to 0, the width will also be 0. So taking you back to calculus, right?
Yeah. Okay.
It'd be the ratio of is the width so narrow and the height so large that it's still a large quantity. I think the Riemann integral would say that it's going to be 0. And then there's other types of integration, like the Lebesgue integral, the other more sophisticated types from advanced calculus and analysis. But that's what we're thinking of. Or at least that's what I think is in place here. An isolated point is okay. An interval is not okay.
What if the interval is just like 2 points, if you will? Wouldn't that still be like...
I think you could still argue that it's still of 0 width if it's 2 points, but if it's an interval of points, I mean, you're confronted with that in probability theory, right? I think. I'm thinking, what's the good example of that? Well, it's if some, I don't have an exact answer in my mind, but it's the same. It's a similar idea, though, about collection of points. So this is sort of a generic model, and it says it's okay to have your passband where you want to reject signals have isolated points where the nulls, where the filter goes to 0 transmission, and it goes up to some very small value, delta 2, for its stop-band attenuation. It's okay to have that, and it's also okay to have some ripple in the passband to make things more, to make it realizable but yet be useful. So a typical thing is to make the passband ripple tiny and to make this very, very small. Like you had the lab where you were designing the equal ripple low-pass filter, right? That has been weeks and weeks, I know, but that's what comes to mind. Otherwise, what you have an asymptotic response, too, that starts off up in here, and then the Butterworth filter, it just asymptotically approaches 0 out at infinity, or in the case of DSP, when we use the bilinear transformation, it approaches 0 at the folding frequency, pi, right? You've gotten exposed to that in the lab because I have the lab doing stuff that we don't do in here. Yeah. There is a chapter on that, bilinear transformation, that I'll never have the time to go through. But so that's kind of a prototype or a concept of what's possible. And I put this in the notes a long time ago, but I thought it's nice to know what you can do, because it keeps you from getting a project in industry and saying, I'm just going to do one of these 4 types and everything will work perfect. You're not going to be able to do that, so you're going to have to, be realistic about it. And this kind of tells you that there has to be realistic constraints then. So now we're going to talk about phase distortion and group delay. Amplitude distortion is understood. I mean, it's just the gain is fluctuating around. But another measure of distortion beyond phase distortion is to take the time to go calculate the group delay. And that's, I'm pretty sure Dr. Song talks about that, or has talked about it in one of her classes. I'm not sure. Maybe it's microwave circuits only, I don't know. But here's the idea. An ideal delay system is going to take an input and delay all of the output by ND samples. So if you look at the frequency response of the ideal delay system, it's just got this linear phase term, e to the minus j omega ND is the phase slope, and then it's got a 1 for its magnitude. So that's what's called linear phase when we just have a pure delay, and linear phase in most cases is acceptable in a system. There's times when it's not acceptable, and I remember my older brother worked in a TV station. He took the time to study for the Federal Communications Commission first-class radio telephone license. Does anybody even know that exists? He took that, he studied for it, took the exam, and then that summer he was working at a TV station and having fun around transmitters and things, and studio stuff too. But I know one of the things was signals that were going into broadcasting were delay had to be managed. And I brought this up before in here, but it frustrates me to no end. Now when we were watching the World Series at my house over a week ago, my son and my wife both like baseball a lot, and I was like, let's get it on 4K because it'll be that much sharper. The 4K channels, though, on Comcast, the audio and the video tend to be really skewed in time. Yes, it's there, but it's very aggravating. You know what I'm talking about? I wish that could be resolved. Maybe it's just a Comcast issue. Maybe if I go with Ting, let's say, remember I mentioned Ting a couple weeks ago? since my neighborhood already has the fiber in it, Ting is now driving around with their authorized contractor trucks. And I saw somebody on my dog walk yesterday getting a cable put into their house from the box, the pedestal out in the street, because they were taking their trench and they were closing it back up again. So somebody's signed up for it, I guess. Will that do better because it's a broader bandwidth connection? I don't know if that issue comes about because of Comcast having issues. I don't know what it is. I'd like to understand it better, though. I'm not going to go work for them, though, but I could call it in and have some layman try to explain to me why it's not working, but I don't think I'd be happy with that. Anybody ever been there with some technical thing? You'd say, I know I could study and I could understand this better. You ask tech support, and you know when they're pretty much not giving you an answer. It's kind of like, you didn't really help me here. But that's because they don't get paid enough money to answer hard questions. That's my feeling. Okay, so now we're going to, I guess we should take the break. Leading up to the next discussion, though, is if you take the ideal low-pass filter and then making it causal, you could put in the delay into the sync function, but you're still going to have it be unrealizable and non-causal, no matter how large you make ND, because you've got the tails of the sync function going out like that, and if you keep shifting it over like this, so there's no tail present from n less than 0, it's still going to impact you. And we went through that kind of in an example, right? We had this, the side lobes still were present in the frequency domain that were very unsatisfying. So the example that we're going to use to get a better understanding of group delay is, and this is, in my estimation, I used to enjoy trying to learn more about this, because where did the term group delay come from? So it comes from this idea here that we have a signal X, which is a signal of interest S, put on a carrier or multiplied by cosine omega naught n. If you haven't taken communications theory or don't know about amplitude modulation or double sideband modulation, this is just going to take from our modulation theorem in Fourier transform domain. If you look at the spectrum of X, it's going to be the spectrum of S shifted up by omega naught and shifted down by omega naught, right? So in a communications waveform in a context of an RF modulated carrier, that's what we're going. That's what's going on here. So S is like the signal of interest. It's like our modulation. So we do a two-term Taylor series expansion and just say that whatever the filter is we're going to pass this signal through, we're going to say that it can be approximated with a constant value and some linear phase related to the time delay that filter is imparting. So we can put this phase shift model into that and say, okay, as we pass this S of n cosine omega naught n through our filter, we're going to see the signal of interest S is shifted by ND samples, and then the cosine wave just gets a phase shift constant and a linear phase, depending upon what ND is. So we're thinking of S as being the envelope of our signal. Signal of interest is S, and it's the envelope, and that's what we're caring about at the receive end or the other end of the link. We want to know, is that intact or not intact? So that's the spectral content of S of n. That is our group. When it says group delay, it's like the frequency spectral content of S as it gets shifted up and shifted down, and it arrives at the other end going through a filter, is that S in contact in, I lost my train of thought. Is it still in good condition? In other words, has that whole group all the spectral components of S, have they all received the same amount of delay? So I'm thinking of the term now from optics called dispersion, but it holds true for coax cable as well, but in optics it makes the most sense. If you're thinking about a signal traveling down a fiber, and I'm thinking of Ting networks now, I guess. I did fiber optics in industry for a little while. If all the frequency components in your information that's being put on to that fiber receive different delays, just like in a coax, the same thing can happen. You get dispersion, and a pulse that maybe corresponds to that S of n gets smeared out, so that you get delay distortion or group delay distortion. So the group is not preserved as it goes through the filter. You get delay distortion. So the way it's defined then is it's minus group delay, GRD, is minus the derivative of the phase with respect to omega. So the units are samples in discrete time domain. If it's a continuous time analog filter, it's going to be in seconds or microseconds, milliseconds, or whatever. So it's the deviation, in other words, it's tau as a function of frequency, how it deviates. If it's not constant, that says different frequencies get different amounts of delay, and it's going to result in dispersion and delay distortion. That's how I like to think of it. Not all traveling at the same frequency. So the whole group of frequencies gets a different delay across its spectral content, and that's not desirable. You want it to be as flat as possible. Is that making sense? Okay. So I have a really neat example here, and I'm going to save that for when we come back from the break. So be thinking about it. This example is something I came up with over 10 years ago, and then in the third edition of the book, they ended up putting it in the book. And I wonder, how did they decide to do that? Because my notes were available on the internet all this time. To me, it was just a no-brainer to do it, and hopefully you'll enjoy it when we go through it, because I think it's kind of cool. Okay, we're back recording again, and yeah, we didn't come back early enough that I necessarily want to quit early, but we'll see where we're at. I want to get to a decent point so we're not in a massive panic for getting the homework done a week from this Friday. So this example is kind of mind-blowing in a way, but I did it in MATLAB originally, but you could do it in Python the same way. I don't even know if I have the original MATLAB code that I wrote to make it work, but it's going to be kind of mind-blowing. What we're going to see, we're going to be putting in two narrowband pulses, but spectrally they're centered on different frequencies. So one's a lower frequency, one's a higher frequency, and then I'm going to rig up a filter that has a lot more group delay, constant group delay in one band of frequencies and a lesser group delay in another band of frequencies. So what I'll be able to do is I'll be able to put these two pulses into the filter, and the one that comes in later will end up coming out of the filter before the one that comes in earlier. Is that mind-blowing or what? I mean, it says the signals are passing each other going through the filter. Is like, how can that be? Well, it's because of group delay. It makes it possible. This is a causal system. There's nothing, I'm not cheating in any way. It's just the nature of it. So this just shows you the significance of group delay. So two narrowband signals, different frequency centers, and so this is the block diagram. We have a low-pass filter, we have an X1 and an X2, and we're going to look in the time domain at Y1 and Y2. And to create these signals, I used a Blackman window function, and that's available in Python, of course, too. Nothing makes this MATLAB specific. It was just the way I did it, and I didn't, you know, I'm telling you, it was written in MATLAB. I didn't take the time to rewrite it, but it would work identically the same. So the center frequency of one signal is at 0.125 normalized digital frequency relative to 2 pi, and the other one's at a quarter. So here's what the spectrum of these pulses looks like. One's at 0.125, like I said, and the other's centered around 0.25. So there's a time domain waveform that corresponds to these pulse spectra, and I'll show you that on the next page. But here is the magnitude response of the low-pass filter that these signals are going through. So both signals get through this filter. There's some ripple in the pass band, but it's not really that large. That would be a fine point to deal with. And I designed an equal ripple filter, so it has 100 dB of stop band attenuation, I guess. It's a pretty large filter. But now what the magnitude response there doesn't show, but what the phase and group delay response does show, in the group delay representation, which comes from the phase response, I put in a all-pass filter array, a bank of all-pass filters that peak the group delay up to around 100 samples over this band. There's some ripple in there, but it's an all-pass filter, which we're going to learn about before the night's over with. All-pass filters pass all frequencies with the same amplitude, but they mess around with the phase. So I've designed this bank of all-pass filters to just peak up the group delay over where X1 is, and where X2 is, it's not really influenced by that bank of filters. This is just an artificial thing, but it's to create an experiment basis. So it's about 20 in X2 and about 100 samples in X1. So here's what the pulses in the time domain look like. They're just a sinusoid that's got a window shape to it, like I said, a Blackman window. So S of n is the Blackman window in this case from what we looked at before the break. So one's at 0.125 and the other's at 0.25, and I've got them set on the time axes at X1 goes in last, X2 goes in first. I think that's what I've got. Yeah. So they reverse their order. Maybe I'm saying that wrong, but the idea is to reverse their order. The one that only gets 20 samples of delay comes out over here. The one that gets the 100 comes out over here. So I said it in the opposite order, but this one goes in first. It's at a lower time index. It comes out last, and this one goes in later, but it comes out sooner. Kind of cool, I think. I mean, now, would you do this for special sound effects? I don't think so, but maybe for phasing or something between two different instruments, you could create some sort of phasing where they're shifting back and forth in time. And it's now in the textbook, which I haven't really studied what they did there. All I know is when I saw that, I said, oh, you guys are doing the same thing in edition 3 that I started doing back in edition 2. So now the next topic, we've now talked about delay distortion. We know what it is and how it can be harmful, at least from what I've told you. In this example, it wasn't harmful because both signals had a constant group delay, but if they were blended together spectrally, then we would have had a lot of delay distortion, and it would have mutilated the waveforms, which is what it does in digital waveforms typically. So now a very simple review concept. We have LCC-DE representations, and we can take that to the Z domain, ratios of polynomials in Z, and we can think about regions of convergence and that sort of thing for getting the output from the inputs. And then we take an example like this right here and just say we have an input-output relationship, we have pole zero, we have region of convergence, and then this exact discussion here is, in this example, I just chose one pole outside, unit circle one inside, and this is just like what we talked about back in chapter 3 and what you did in a homework problem too. How do you make it causal? How do you make it stable? In this case, causal is not stable, and non-causal is stable, but it's not realizable in real time. Okay, just a quick review. This topic is just something I threw in here for completeness. You've all seen the Routh-Hurwitz stability criteria, probably in 3205, right? Where you work with polynomials, numerator and denominator in the S domain. So what do we have for the Z domain? We have these two guys, Schur and Kohn or Kuhn. I'm not a pronunciation expert, but their stability test works with a polynomial, and the idea is the same as in the S domain with the Routh array and so on. You're trying to see whether or not any of the roots in the S domain are in the right half S plane. In the case of the Z domain, it's any of the roots are outside the unit circle. That's what it all boils down to. And I'm not going to spend really any time on it, just to say here's the discussion. You go through an algorithm kind of like you would in the Routh array, and you end up with looking to see whether or not there's a so-called reflection coefficient, which is greater than 1, and that indicates that you have a root outside the unit circle. I don't, for me and my purposes, I'm happy using roots. Like in MATLAB and Python and Julia, the roots function just tells you, are there any roots outside the unit circle? And that's, like Z-plane shows you that too. So I just use that, but this was just for completeness, an example for completeness as to how it works. We're not going to do anything with it, but it's in here. This we are going to do something with. So inverse systems. I've frequently had an inverse systems problem on exam too, so I want to make sure I have my options open by talking about it. So what is an inverse system? An inverse system undoes what a system does. So if you take h of z times h inverse, you get back 1. So that means h inverse is 1 over h of z. Sounds simple enough, but the peculiars are that, first off, if the system manages to null a whole band of frequencies to 0, there's no way that you can get those back again, because you'd have to have infinite gain. So that only makes common sense. And another more practical aspect of this is, if we have a rational function for h of z, then the inverse of it, 1 over h of z, has to have, to be realizable, it has to have poles inside the unit circle. So, as a matter of fact, we have to have, the ROCs have to overlap in order to have the inverse exist, because we have to be able to say that h of z times hi of z will be stable and will have a region of convergence, which is the exterior of the largest pole radius. So a simple example is right here. I'm going to jump over to my notebook. This is the first one that's in here. Oops. This is the example we're looking at. I just simply put in some coefficients. In this case, I'm going to use B1 and A1 for the system, and then B2 and A2 are just flipped over to make the inverse system. So here, I use a function from the module IIR design helper, and there's also FIR design helper, but IIR design helper is an easy, simple way of overlaying plots. You might decide to try it out sometime or have a use for it. So here I'm going to get the frequency response of all three systems by just putting in a list of numerator polynomials B1, B2, and B3, and then a corresponding list of A1, A2, and A3 out of that. So B3 and A3 is just the ideal system you'd get from h of z times hi of z. So there's there's the response. It just says that, okay, the distorting system rolls off and continues to roll off, but not by very much after a certain point. The inverse system has to flatten that out and get you back the green response. So that's the idea of the equalizer or the inverse system. The inverse system flattens things back out again and makes it look like there is no distortion in the system. And I'm pretty sure in 2610 there was a lab problem on this. I remember using it at least once, maybe every time I taught the class. I don't know. Does anybody remember? There was a pretty cool lab on inverse systems. I know, it's been a really long time for me, but I just remember it. So a little bit further down in the notes, but not right at this instant, we're going to be confronted with how do I get an inverse system if the system is non-causal. So in this case, there's h of z. We've got a 0 at 2 and a pole at 0.9. So if we create the inverse system, we're going to have a pole at 2, which is not going to be acceptable to be causal and stable, right? Am I making sense? That's correct, isn't it? So how do we do this? Well, we'll learn about all-pass filters. With an all-pass filter, basically this problem comes down to modifying the system from non-minimum phase to minimum phase. And when we make it minimum phase, all the zeros will have to go inside the unit circle, just like the pole already has to be inside the unit circle. So then if we invert it, we're good, because both poles and zeros are inside the unit circle. When we flip it over, poles and zeros are still inside the unit circle. So how do we do that? We're going to talk about the all-pass filters a little bit later, but what's going to happen here is that this, when it goes into the denominator, this numerator, 1 minus 2, is going to become 1 minus 1/2. So we're going to take that pole out there at 2 and make it its conjugate reciprocal, which flips it inside of the unit circle. Explain that with an all-pass filter here in a little bit, but that's what happens. So if I do that here and run the same simulation, this is what's happening. This is the original system. This is the inverse system. And in this case, because I haven't done everything totally correct in terms of gain, the gain of the system is not flat. It's not unity. But really what it is that I need to put a 2 in here somewhere. So I need to put a 2, on why do I know that's true? I look at this and say it's nice and constant, but in dB it's around 6 dB. And what is a 6 dB factor gain-wise? It's a factor of 2, right? So I'm going to put an extra 2 in the denominator up there, and that's going to lower this down. So if I rerun this again, now it's perfectly flattened down, and we'll understand why this has to be in here. This was a seat of the pants all-pass filter. All I did was flip the pole outside the unit circle inside. I didn't do it entirely properly. I was missing this gain constant. And I'm telling you this right now because this will be a factor in the homework problems and will also be a factor on exam 2 to make sure that if you have to develop an all-pass filter, you get the gain correct. You do the gain correction properly. So I got some more examples in here, but I'll think about whether or not I want to go with those right now. And I'm going to probably not do that. It's interesting, but I'm going to move on to this next topic. Need to get more on the page. So the next thing we have already learned was getting impulse response by by taking the inverse Z transform of the system function. And we know that we may have to do long division, so we might have a term like this, and then we'll have the simpler repeated poles. And this example is just very simple, no repeated poles, but we just get the impulse response directly. Again, not a whole lot more to say about this. It's just something that is just part of the review and part of now what's all on the table. And I say all on the table, I mean everything that's been done is now available for us, and we can explore other properties that were not done along the way. So the next one, frequency response for rational system functions. We've actually spent quite a bit of time with that. We're going to be a little bit more formal right now. So we have, in terms of poles and zeros, this would be the frequency response where CKs are the zeros and DKs are the poles. And if B0 and A0 exist in the original numerator and denominator polynomials, they are pulled out front. And then we can get access to the magnitude response by finding the magnitude of each of the pole terms in the zero terms in the numerator, each of the pole terms in the denominator, plus the B0 over A0. We can do that in dB. And attenuation is the negative of gain, just a known fact. And then we can get the phase by getting the contribution of B0, A0, and positive phase for each of the zero terms, and subtract the phase from each of the pole terms. And then book will talk about, and I've talked about principal value. Principal value is what you always deal with when you're doing the phase function in Python, or the angle function, and it runs between minus and plus pi. So if we have, say, a linear phase FIR filter, which we'll be getting into later in this chapter, has this magnitude response. If we wanted to take its phase, which would be modulo 2 pi, so it would be running between plus and minus pi, and we wanted to unwrap the phase, this is what the real phase looks like. It continues to fall, and then it just zigzags around there because something we're going to talk about. There's a zero on the unit circle at these frequencies that's causing those jumps to happen. But this is a characteristic of a linear phase filter that we'll be getting into at the end of the chapter. This slope here, all of these segments here all have the exact same slope. That's a very significant property. How do you unwrap? If you have wrap phase, which is what you get if you just take the angle or the phase, depending upon what language you're using, it looks like that. And then when you unwrap it, you get this plot up above. And so the unwrapping function is a step function that goes along there and senses that it should be unwrapped. I don't really want to get too carried away with this, but I've worked on some digital communications problems where this unwrap function is something that's important to have to do. I've had to actually put it into code, an unwrapping function. So now we're going to go on to a topic that is also in the homework to some extent, but likely to be on exam too, geometric evaluation of the frequency response. So we kind of pick up from where we left off here. We have our numerator and denominator. We have z minus c sub k, and now we're going to substitute for z e to the j omega, and then we can write the numerator and denominator as products of vectors, vector magnitudes, and the vector is, it's this terminology here. We have e to the j omega minus c sub k. So just like in physics, if you're taking a vector in the complex plane, it's going to be at a location e to the j omega, and it's going to connect to the point c sub k. And we're going to be doing that here next, the idea of a geometric evaluation. And this is something that maybe Dr. Trimboli, who taught you 3205, did you ever do pole zero geometries in S-plane?
I think we touched on this right at the very end.
Okay. It's just a kind of a practical comment, and it's probably something that, to me, it has to do with two things. Number one, a long time ago, we didn't have calculators, we didn't have computers. You could just get an idea of frequency response by knowing pole and zero configurations, and so it's an easier calculation means. And then another thing is just common sense, saying I want to look at the pole zero plot because I can understand maybe what's good or bad about my system if I just know the pole zero configuration. So that's why I'm a big fan of Z-plane. I wrote that function because I missed it when I switched from MATLAB to Python. I didn't have a Z-plane function, so I wrote one. So we'll just take a really simple IIR or FIR system. It's just a single zero, 1 minus r e to the j theta. So that is 0. That would be like Z1, let's call it. So if we look at getting the magnitude and then the phase response, both of them are on here. Phase response is just the angle that these vectors make to the positive real axes, but we have 3 vectors in here, or 2 vectors. I mean, we have that one, and we have the z in the denominator. So in terms of our vectors, we have this vector and that vector. So if we're going to draw a picture of that, we're going to have our vector links draw out to the locations in our model here. We have, what I said earlier was wrong. And from the physics standpoint, you start at the location of where the subtracting component is, and you go to the location of the positive component. So we're going to draw vectors on here. We've got a z in the denominator, so that's a pole sitting here. It's going to go up to I think I did that wrong. Yeah, I don't want V2. All the action is going on right over here. Oops. Because we have to go from 0, that's our length V1, and then our length V3, that's the numerator, that's going to go from this pole, or this 0, over to here. So what we want to be able to do is track the ratio of those magnitudes as a point on the unit circle is moving around. So as we move this around, the lengths of these vectors are going to change relative to the fixed poles and zeros in the system. And then it's the ratio of the magnitude V3 over V1 that controls the magnitude response. And then the angles that are made control the phase response, angles to the positive real axes. So that's the other notes that I have in here, the phase shift angles. C3 and C1, I guess, is in here, but I'm not doing anything with it. I just picked a couple different values, though, in this case. I didn't want to do that. I'll delete the whole thing. At any rate, I'm going to show you another software tool. Another way of viewing the geometry idea is with a 3D surface. So you can think of having, wherever there's a pole in the system, you have a rubbery surface down here, and it's getting pushed up to infinity. and wherever there's a 0, it's getting tacked down to 0. So it's the overall height of the rubbery surface around on the unit circle. In other words, what is down here is the magnitude response. So when I get close to the 0, I'm going to have a dip. When I get close to a pole, I'm going to have a high point. And you can write this out analytically for this simple configuration to get the magnitude. You can write out the phase. You can even go ahead and take the derivative of the phase to get the group delay. So this tends to be how this works. If you pick a different value theta, say theta is 0 for your 0, then you can see that you're going to have the magnitude response is going to go through a dip at 0. Let's see, that's this case. And then as you move that 0 around, it'll dip at a higher frequency. So this is okay for my notes, but I have to do more to satisfy myself. I have an animation program I'm going to run now. So I'm going to go ahead. Remember the Zojo application. So there's an application. And I can't put these on the website because they're too big with the DLL libraries. I actually have Linux, Mac, and Windows versions, but I can easily send them if anybody's interested on Slack. I can just drop them on there. And the way Zojo applications work is you don't have to use an installer. You just plop it right in here. I would send it to you by just lifting out of this folder, and then you'd have some support files, and then you can run it. You have to agree that it's safe. You know, when you run a new app on Windows, let's say, it'll say, do you trust the author? So you have to trust me to not have written bad stuff into the code. But so here's our example right here. There's a pole sitting here. There's a 0 sitting back here. I could define it differently, but what I can do with this app is I can move around. This is the e to the j omega knob right here, and I'm drawing a vector from a 0 out there and a pole in there. But like I said, I could change this if I didn't like that. I could change the coefficients in the denominator. I could, for example, no, that's not what I wanted. I want that to be, oops, I didn't want to do that. I just killed it. I did this earlier, and how did I make that work? Yeah, I can do that. Okay, this is a little bit more like what we were just looking at in the notes. So the 0's out close to the unit circle. There's a pole sitting there. So as I sweep around, you see the gain comes up. I can plot the gain in dB if I want to, and I can manipulate my plot window like that. And then I can see the phase is going to flip, because we know that's true for a real system, right? When we're on the negative frequency, the phase flips. Magnitude stays the same. So we can pick something maybe we'd like to see, like a 5-tap moving average filter. Remember, it has the 5 zeros around on the unit circle. It has nothing at DC, and then there's 5 poles sitting in here. So as we move this around, maximum gain is right there, because the product of all of these red vector lengths divided by the product of all the denominator vector lengths, which are all 1, by the way. As I move the blue dot around, these vector lengths never change, so it's just the product of these vectors. That's the peak, and then the rest, happens as I move things. In particular, because I have zeros on the unit circle, I'll get a 0 when I'm right where that first 0 is, and so on, and so forth. Pretty obvious? But it took a little bit of work, and I was passionate about this many years ago. I wrote the code for this just because I want to learn how to write Windows applications with hotspots and other things for the mouse cursor and other little things to work with my scroller window. But let's just take, I don't want to take a lot more time, but we are going to be looking at all-pass filters here shortly. But here's some other types of filters. Is there some type of filter on there that you're curious about, what it would look like in this tool? Okay. We're going to spend a lot of time with all-pass, but okay. So a 5 fifth order all-pass. So what the all-pass filter does is it places, in order to be a realizable filter or causal filter, all the poles are inside the unit circle, and then the zeros to create an all-pass section are all at conjugate reciprocal locations. So that one is like at minus 0.8. This is going to be at minus 1 over 0.8, and so on and so forth. Pairwise is all that matters for them to be all-pass, just with respect to the conjugate reciprocal. So as I move around here, the geometry, whether it's 1 all-pass section in this, or 5 as it is here, it's just the gain is fixed at 1. The phase, however, is, you know, doing whatever it's going to do because of the characteristic of the geometry, the angles that these vectors make. The numerator angle, which would be the real axes, here swung around over to there, that's going to be a positive, and then the angle this makes, extending that in the positive direction, that angle, and then for all of them likewise, how that would work. So probably the best thing to do if you really wanted to see that would be to just put down, got to be careful here, nope, I can't do that. I'm trying to remember how to do this. I put this in custom, I guess, to do that. Say what's 0.8, 1 over 0.8 is what? I have to write it as a decimal number here, I think. I'm not positive anymore in this tool. I don't think I can just write minus 1 over 0.8. No, that didn't work. That's back over there, so now I can make this work though. I just don't want to spend a lot of time on it. Yeah, 1.25. When I get tired, my brain's not working too good. So I'm going to make this there we go. So that's the right relationship, right? That's at 0.8 and that's at 1.25. So now, as I move around, what's happening here, whether I'm here, the ratio of the red to the green is the same as it is when I'm right there, anywhere around here, including right there. That's the nature of the all-pass filter. The geometry is such that it's always going to be constant like that. Intriguing? Or is it just a game? Every time I push up a YouTube video for this class, I have to fill out a bunch of forms on YouTube. And one of them is does this video show any children? You can't have that in your video. And number 2, I have to select a box. Is this meant for kids or is it not meant for kids? So I always select it's not meant for kids. And then it goes through more stuff, more questions, and then it has to get approved then because they scan it to see if there's anything that I did to break the rules. If you ever push videos, and some of you probably have, you got to go through that process. But this is making me think, I don't think kids would consider this to be a game, but I kind of do. I mean, I created it that way, so. And also, yeah, you can get a listing. If you wanted to factor the poles out, you could see poles and zeros listing in polar form or rectangular form. I'm going to come back to this, but I'm going to just shut it off for the time being. So back over to the notes. So what happens if we put this next example, what happens if we put a 0 right on the unit circle somewhere? We just were looking at that case. So what happens when you have a 0 on the unit circle, you think about the angle is going to be if the e to the j omega point is approaching from the right side of that 0, there's going to be an angle vector that's going to be drawn around for the numerator, and then there's going to be, as it passes by, it's going to be identically indeterminate right at 0, and then as it passes by, it's going to be on the other side. It's going to be over here. So you're going to have this angle or this angle that goes all the way around. So the difference between those two angles is what? Just thinking about what's happening there. You have to think geometry, but just before it gets there, the angle starts on the positive axis. It has to go all the way around almost to 2 pi, right? But if it's just past that point, it only has to go around to pi. So whenever you encounter a 0 on the unit circle, what the math here says, it's approximately going to be this. And I just used epsilon in here, but phase jumps by pi radians when that happens. So when we've seen the plots earlier tonight in the low-pass filter where it had zeros on the unit circle, there was a jump of pi every time it happens because it's zooming past a 0. That's, you know, we're learning a bunch of facts about how things behave. So there's the picture of that one. Okay, the next step, though, is to take and put the 0 just outside the unit circle. So when it's outside the unit circle, then as you go past on either the j omega axes, you're going to pick up a 2 pi jump. And I don't have a picture drawn of that right here, at least I don't think I do. I guess if we're inquisitive, though, we have to go back here and try this. Put the pole at 0, and we'll put this at okay. My algorithm isn't quite working right in terms of how it's plotting the angle down here, so it doesn't always catch it properly, but it is. If I fiddle with it, it will jump 360 degrees at that point. It has to do with, you know, the real axes from here. I have to go look at this more diplomatically, I guess. We start there, positive real axis, come all the way around to get to there. Whereas if we're down here, then draw the real axes out from there. Right up to there is approximately just a little bit positive, whereas the other direction, it's starting from there. It has to come all the way around almost to 2 pi. So I think in the limit it's 2 pi. Is that a good enough argument? I mean, the reason why that's of interest is because it tells you something about the phase you can expect to see. And maybe I should have run a more complicated example. So here's an elliptic bandpass filter. So there's the response of the filter, and if I put this in dB, ripple in the pass band, stop band, and then I guess in this case all the zeros are on the unit circle again, so that condition doesn't hold in this type of filter. I'd have to go with an equal ripple FIR filter. There are poles, though, that are around here inside the unit circle, but they're never outside the unit circle for stability reasons. So now when you look at a filter, though, you have a new understanding about all these vectors that are the product in the numerator and the denominator that are changing with frequency. Then I carry that on to the conjugate pole pair, and conjugate pole pair just says there's a pole up above and down below. What sort of characteristic does that have? And if it's got 2 zeros, that 0 to balance out those 2 poles, then you can have this for your 3-dimensional plot of the surface and show that the 2 zeros are creating a point right at 0 there, and then you've got these 2 poles pushing up on the rubbery surface, and as you zoom by on the unit circle, cutting down into the surface, you're going to create the peaked response that you see right there. And the phase is going to be tracking along with that too. And this can be written out analytically all the way through magnitude, phase, and group delay. Some of these things are kind of interesting if you wanted to write a piece of software that would be a closed form solution for an arbitrary configuration of poles and zeros, and you wanted to analytically have a solution. This would be a way of getting there, because you've got the cascading property that you could use to get this response. I've taken advantage of that somewhere, but I don't remember where it was. Okay, the last one we'll look at is the comb filter, which we already looked at, moving average filter. In this case, I've got 8 taps in it. So we looked at this really early on. And if you look at the rubbery surface for that, it reminds me of my backyard. Why do I say that? Because gophers and other voles and things like to dig around trees. Have you ever noticed that? They like to dig holes. If you're a homeowner, you get aggravated with that. But they're digging around your tree. So these are like the gopher holes around, and this is the tree trunk, because you've got all those zeros at 0 that are just blasting it off to infinity, super infinity, right? Because of all the poles that are sitting there. So when you sample that, we get the classical result. Because you don't have any 0 here at DC, we get the pass band in there, and then the action takes place. But here, we can see the pi jumps occur every place. There's a 0 on the unit circle as well. This resonator we already kind of talked about, but okay, I'll resist. I won't entirely resist. There's another program on here called TZ Tool, and this one lets you, in MATLAB used to have a version of this. That's what inspired me to write this. But this one lets me do what I was just talking about. Suppose we wanted to see what what would happen. So I'm going to get rid of the conjugate pole. I'm going to add pole out there. Then I'm going to get rid of that pole, and I'm going to put in a conjugate pole. And I guess I have to get rid of this again. I think I wrote this in the code so that I don't have something blow up. But now I can do what I was just talking about in the example. The two zeros that are at 0 and at pi are trying to make sure that this response tacks down to 0 at either end, and then the poles that are peaking up here and here cause it to have its passband. This is another geometry way of thinking of things, so that makes sense, doesn't it? You could do that. And of course, I'm only plotting from 0 to pi, but the magnitude would be the same. I could look at it in dB if I wanted to. And there's going to be a phase swing because as you go past a pole, just like if you go past a 0, there's going to be something that's going to change rapidly, right? So if I drive this in closer to unity, there's going to be a much steeper phase change in that neighborhood. So if I wanted to add another pole pair in there, I could start forming a pass band. Is that kind of making sense about how a Butterworth or a Chebyshev could be formed? And then if you wanted to add some more zeros in, you could start making like an equal ripple, a elliptical filter that would start putting in the zeros. Obviously, I like entertaining myself, so I created this just to kind of get better feel. But I think it's important to understand how some of these things work. So, any questions just on playing around like this? It could be better than a video game, I don't know. Okay, back over to here. So now the big topic, just for the last bit of time here, which is where the all-pass filters are going to come in, is this totally brand new concept of relationship between magnitude and phase. And it's not going to be as bad as a random process, as an ensemble of sample functions. This is just going to be a more minor mind-bending thought process. But so there's a constraint for a system described by an LCCDE. There's a constraint between the magnitude and phase. If the magnitude response is known and the number of poles and zeros is known, then there's a finite number of choices for the phase. On the other hand, phase response is known and the number of poles and zeros is known, then to within a scale factor, a finite number of choices exists for the magnitude. So this just makes you think of, of possibilities, and the fact that it's had to say a finite number of poles and zeros known is because if we don't tie things down like that, we can hide all-pass filters inside of this development, as many as we want, and nobody even knows they're there. They could be just sitting inside there because of the all-pass nature. It'll mess with the phase, but it won't mess with magnitude response. So the way this gets looked at is you consider the magnitude squared of the frequency response. So the first thought there is that's going to be h of e to the j omega times h conjugate of e to the j omega, because that's magnitude squared of a complex quantity. And then taking that to the z-plane, that's going to be h of z, and then it's going to be h conjugate of 1 over z conjugate, which seems redundant, but it's necessary because of the way the theorems work with complex quantities. We have to have the extra conjugate in here. and then we're evaluating it on the unit circle. So if we write that out as this form of h of z times h conjugate of 1 over z conjugate, then in terms of poles and zeros, this is what we have. We have all the poles present, all the zeros present, and then we have all of the conjugate reciprocal poles and zeros present. And the conjugate reciprocal means that poles, if we were talking about a unit circle, that says it's going to be on the same angle because of the conjugation operation. The 1 over operation moves it from the inside to the outside, but the angle flips, right? But if you conjugate it, then you bring the angle back again. So these are just some of the observations in the sub-bullets there. But if h of z is causal and stable, then the poles of h of z must start off inside the unit circle. The zeros could be anywhere. So here's what a 3-pole, 3-zero system would look like. We would be able to say that if we look at this picture, we're seeing all the poles and zeros in their conjugate reciprocals. If we wanted to identify which are of the real causal system, the 3 red X's there are the real system, right? Because they have to be inside the unit circle. But then we can mix and match where we pull our zeros from. We could pull this 0 instead of this one. We can pull this 0 instead of that one. We can mix and match along the way. Does that make sense? So these are the combinations. We can have case 1, where all of the zeros are also inside the unit circle. That's the minimum phase extreme. Mixture would be case 2 and case 3, and then the maximum phase is where we push all the zeros outside the unit circle. This is just the terminology, minimum, maximum phase. And how does maximum of phase even come into our minds? Well, it might be a situation like in that inverse problem we were looking at earlier, and in a mobile radio channel, it could be that the signal that has to travel the greater distance has less attenuation on it than the signal that's nearby. The signal nearby may have to go through some obstacle that attenuates it. So that means we can get a situation where we have a non-minimum phase channel. I'm just using that as an example where non-minimum phase can occur. So if we let h of z contain this factor right here, we can alter our choices for h of z. We won't alter the magnitude response, but we'll be able to alter the phase response. So this is called an all-pass section right here. This is the way the book defines it. And then if you rewrite the all-pass section by putting the z to the -1 along with the coefficient, you end up having to pull, let's see, pull that out in front. And that was what was missing in that equalizer example I ran earlier. Remember, the gain factor of 2 was missing? That's because I made that change and I didn't properly do this. Or if it was the denominator, it would have been that way. But that was what was missing there. So that's what's in here, though. This is the nice, simple way to write it out. But if you wanted to implement it, this is the way we think of implementing it in, say, Python or something. So that factor comes out of there, that gain factor comes out. Why is it unity? Well, what we can do is we can take and replace z by e to the minus j omega. That's what I'm going to do here. So I'm just replacing z to the minus 1 by e to the minus j omega, a conjugate a, and then e to the minus j omega. And then we can factor an e to the j omega out of the top side, and it's a magnitude, so it'll be the magnitude of e to the j omega. And what we're left over with is 1 minus a conjugate of e to the j omega, 1 minus a of e to the minus j omega. And what can we do to make those cancel? We can just visualize that if we pulled the conjugate out of here, added an extra conjugate, let's say, then this would become a, and it would, in the process of doing that conjugation, this would become e to the minus j omega. So they will, that is unity, is what it comes down to. Is that believable? That's what happens mathematically. They're equal. So any number of all-pass filters sections can be present, and when we're looking at it as a C of Z, we cannot see them because the all-pass sections end up having conjugates of the polar zero that create them, and if we create conjugates of those to put in the C of Z system, they kind of wipe themselves out, so they're transparent in that C of Z function, which I think is also kind of bizarre, but it's the way it works out mathematically. So it's what it means to have an all-pass system. And where did I say this? Yeah, I didn't say it. Don't say it yet in the notes. But the property is magnitude is 1. This is the form of the first-order all-pass filter, and the higher-order all-pass filter can be shown to be this form. You take the coefficients and you reverse them in the numerator from what they are in the denominator, and that defines an all-pass as well. Let's take a quick look at that. I did some more geometry stuff in here, but let's take a look at this all-pass. So here's using z-plane, minus 1/2 and 1. Reverse the order of the coefficients, 1 and minus 1/2, so that's correct. That's an all-pass. And then I just arbitrarily say, let's do a higher order design. Let's just put in 1, 0.2, 0.4, 0.3, and then just use Python's colon operator with a minus 1 at the end, just reverses it. And you can see that it's reversed here. And that's also all-pass, the third order all-pass, just arbitrarily created though. It's got that property though. And if I go ahead and say evaluate the frequency response using freq at 3 frequencies, 0, pi over 2, and pi, I will get 1 for all of them. Or if I just take these filters and look at the dB phase and group delay, I'll see 0 dB gain. There's the goofy phase response I'm getting for that thing, and there's what the group delay looks like in samples. You're going to be playing around with these filters in the homework. If you want to get on board with it quickly, you can decide different things to do. Since I'm just about out of time, I'm going to go look at something that's on the website though. And also rescue my water bottle so I can get my throat working again. That squeezing operation is hard for my hand to do still. But if you look under course materials, I have this link down here, Exam 2 Example Problems. It's not super rich, but it's got some information. It's got things that you've already done, but it's encouraging you the way I'd like, if I ask you to draw pictures like this, this is what I want you to do. And this type of problem, when it appears on Exam 2, I'll give you the spaces to draw it out. So you'll be able to just draw on this sheet, scan it, and put this in your solution for that type of problem. And I gave a couple of examples of that here. But what we're going to be getting to, and but I'm not formally going to do right now, is any system H of Z can be written as a cascade of a minimum phase and an all pass. And eventually we'll see that it can be written as a minimum phase and a linear phase cascade. But for right now, I have a few examples of the minimum phase all pass. So here's the minimum phase, and how do we make this an all pass? I mean, we put an all pass of that type in, and when we cascade these together, this gets canceled by that, or depending upon how you want to visualize doing it. If you started off with the pole right here, and if this is the 0, so I make the minimum phase, and then when I put it cascaded with an all pass, this pole will cancel that 0, and it'll replace it with a 0, which is out there. So that's how you can synthesize a non-minimum phase system with all pass sections.
I think I understand like how you get from one to the other, but I don't understand why we would do that. I don't really see a correlation between, like, I mean, one of them is like the minimum phase.
Well, we needed the minimum. Well, let's take the example with the equalizer, because that's a good case in point. The equalizer, if we had a filter here that we wanted to create the inverse of, can we create the inverse of this filter and have it be causal and stable? We can't, because that 0 is going to be outside the unit circle, and it becomes a pole outside the unit circle. But if we can get its minimum phase equivalent, which is what this is, this can be inverted, because this becomes a 0 and that becomes a pole, and we're in good shape. And that's exactly what I did in that example earlier.
Yeah, but why is that equivalent? Does it have the same like magnitude?
Yeah, the same. It'll have the desirable magnet. It'll have unity magnitude. It has a different phase though.
Okay.
But the point is, we can do this. We can make a causal inverse. Without it, we're stuck. We can't do anything. We can't make it be causal because of stability reasons.
Yeah.
And then there's other properties of minimum phase systems. This is kind of an exotic topic, though. I mean, it's not a life-saving thing. It's just sort of this is kind of interesting thing. So I just thought I'd point out that this page is here if you want to. And I did the linear phase, which we haven't gotten to yet, but then I also have another example that's got just more poles and zeros in it, and how that would work. This is not a major theme of the chapter. It's just one of the more new concepts, topics. So I think I should stop here, though. So what I want you to do between now and next week is obviously start doing the homework. Keep working on the project, though. I didn't take time for questions on the project, but I want you to keep working on it. Don't get flustered about having the homework done, because we will have Tuesday and the homework will be due on Friday. So we'll have time to do that. I'll put hints out for it probably around Tuesday of next week so you can finish it. But we're headed for the take-home exam next week, probably by Thursday. I'm going to start thinking about my take-home exam problems tonight while I'm eating. And then the project, getting that thing nailed down. And I don't know where anybody's at. Has anybody tried the Pi Audio parts yet? Is it working for you?
Yeah, I mean, I got it working in the lab, so
Okay.
that was easier for me to get that working.
Okay.
I struggle getting it working, but I use the